In 1453, an artisan in Isfahan pressed a ceramic tile into wet plaster on the wall of a shrine and created a pattern that Western mathematics would not have a name for until 1974. In 1982, a material scientist in Maryland wrote 3 question marks in his lab notebook next to a result that every textbook on the planet said was physically impossible. And 4.5 billion years ago, before the Earth existed, atoms inside a colliding asteroid arranged themselves into a structure that the scientific establishment would spend the next century insisting could not be real. Those 3 events have nothing to do with each other, except they do. They are the same discovery made 3 times across 5 centuries and 4.5 billion years by people who never met and disciplines that never talked. And the thing they all found, independently, is a kind of order so strange that explaining it requires mathematics in 6 dimensions, not as a metaphor, as the actual, standard, peer-reviewed framework that working crystallographers use every day. Tonight, we are going to follow that thread from a mathematician cutting paper shapes at a kitchen table, through the most bitter scientific feud of the 20th century, into a museum in Florence, across a Russian wilderness, and all the way to a question about the geometry of reality that nobody has been willing to ask out loud. Get comfortable, settle in, and if you are not subscribed, go ahead and join. If you want more of this kind of thing, across physics, mathematics, deep history, and the parts of science that don't make it into the classroom, that is what the Patreon is for. Stay to the end of this one, because where the 6 dimensions lead is somewhere I genuinely did not expect when I started reading the papers. Let's start where it started. In 1992, the International Union of Crystallography did something it had never done in its entire history. It changed the definition of a crystal. Not refined it, not expanded it, changed it, deleted the old one and wrote a new one from scratch. The old definition had stood since the 1890s, since Fedorov and Schoenflies and Barlow had classified all 230 space groups, and the field had collectively agreed that the question of what a crystal is had been answered permanently with mathematical proof. A crystal was a solid with a periodic 3-dimensional arrangement of atoms, repeating, predictable, translatable. You slide the pattern in any direction and it maps onto itself perfectly, forever. That was the definition taught to every chemistry student, every physics student, every material science student on the planet for 100 years. It appeared in Kittle's Introduction to Solid-State Physics, in Ashcroft and Mermin's Solid-State Physics, in every crystallography course, in every university, in every country. It was not presented as a working hypothesis. It was presented as a fact, backed by a mathematical proof, as settled as the value of pi. And in 1992, they had to throw it out. The new definition, published in Acta Crystallographica A48, pages 922 to 946, replaced over a century of certainty with a single operational sentence. A crystal is any solid having an essentially discrete diffraction pattern. No mention of periodicity, no mention of lattices, no mention of symmetry restrictions. If it makes sharp spots when you shoot X-rays through it, it is a crystal, and the committee that wrote the new definition explicitly called it interim, provisional, because they could no longer claim to know the full scope of what order looks like. They could no longer claim that their taxonomy was complete. The map had been redrawn, and the territory was larger than anyone had assumed, because 10 years earlier, on a Tuesday morning in April, a man in a government laboratory in Maryland had looked through an electron microscope at a piece of rapidly cooled aluminum alloy and seen something that the mathematics said could not exist. And it was not a mistake. It was not an artifact. It was not a contaminated sample. It was a new kind of matter, a kind of matter that had perfect long-range order, sharp diffraction spots, beautiful crystalline precision, and absolutely no periodicity whatsoever. The atoms were arranged in a pattern that never repeated, not in any direction, not at any scale, not ever. And the symmetry of that pattern, tenfold rotational symmetry, was not merely unusual. It was forbidden. The crystallographic restriction theorem, which you can prove on a napkin with about 4 lines of geometry, demonstrates that the only rotational symmetries compatible with a periodic lattice are 2, 3, 4, and 6, not 5, not 7, not 10. The proof has been known since the 19th century. It is airtight, and this man was staring at a diffraction pattern that violated it. To understand how radical this was, you need to understand how certain crystallographers were that this could not happen. The crystallographic restriction theorem is not a conjecture. It is not a hypothesis. It is a geometrical proof derivable from first principles that requires nothing more than the definition of a lattice and about 4 lines of algebra. If you have a periodic lattice in 2 or 3 dimensions, meaning a pattern that repeats by translation, then the only rotational symmetries that lattice can exhibit are orders 1, 2, 3, 4, and 6. That is it. 5-fold symmetry is out. 7-fold is out. 8, 10, 12, all out. The proof was known by the 1890s. Fedorov, Schoenflies, and Barlow had classified all 230 crystallographic space groups, every possible way that atoms can arrange themselves in a periodic crystal, in 3 dimensions, and the field considered the question closed with the finality of a mathematical proof, which is the most final kind of closure there is. This was not a matter of opinion. It was not a working assumption waiting for better data. It was geometry, and geometry does not change. Except, of course, when the premise is wrong, when the premise that all crystals must be periodic is wrong. Then the theorem still holds perfectly, but it becomes irrelevant. It tells you what periodic crystals cannot do. It says nothing about what non-periodic crystals can do. And that distinction, the distinction between impossible for periodic structures and impossible for all structures, is the gap that the entire field fell through for 100 years. His name was Dan Shechtman. He was born on January 24th, 1941, in Tel Aviv, in what was then the British Mandate of Palestine. His maternal grandfather, Ziv Ashur, had immigrated from Ukraine in the early 1900s and set up the first Jewish printing house in Palestine, working alongside figures who would become Israel's first prime ministers. Shechtman served 2.5 years in the Israeli military, trained as a sharpshooter, met his future wife Tzipora during his service, and then studied mechanical engineering at the Technion, Israel's Institute of Technology, taking his bachelor's, master's, and PhD there between 1966 and 1972. He has said that his childhood hero was Cyrus Smith from Jules Verne's The Mysterious Island, an engineer who could build civilization from raw materials on a desert island. After a postdoctoral fellowship at the Aerospace Research Laboratories at Wright-Patterson Air Force Base in Dayton, Ohio, studying titanium aluminides, he joined the Technion faculty in 1975. He was on sabbatical at the National Bureau of Standards in Gaithersburg, Maryland, when everything changed. And what he wrote in his lab notebook that morning, under sample number 1725, in his own handwriting, was 3 words and 3 question marks. Tenfold, that was it. 3 question marks. Because he knew the rules. He had derived the crystallographic restriction theorem himself as a student exam answer at the Technion. He knew, with the certainty of someone who has personally worked through the proof, that what he was seeing could not be real. The sample was an aluminum manganese alloy, roughly 14 weight% manganese, produced by a technique called melt spinning, in which molten metal is sprayed onto a rapidly spinning copper wheel and cooled at rates exceeding 1,000,000 degrees per second. The technique, performed by an NBS technician named Frank Biancaniello, was designed to produce unusual metastable phases, alloys that would not form under ordinary cooling conditions. Shechtman was systematically surveying these rapidly solidified alloys with a transmission electron microscope, looking for interesting microstructures. What he found on sample 1725 was more than interesting. A transmission electron microscope works by firing a beam of electrons through a thin sample and collecting the diffracted beam on the other side. A crystalline material diffracts the electrons into sharp spots, arranged in a pattern that reflects the internal symmetry of the atomic lattice. Shechtman knew how to read these patterns the way a musician reads sheet music. He had been doing it for years, and the pattern from sample 1725 was wrong. Not ambiguous, not noisy. Wrong. 10 spots arranged in a perfect decagon, with smaller spots at precise angular positions between them. Tenfold rotational symmetry, as clear and sharp as any diffraction pattern he had ever seen from any crystal. But he also knew what he was looking at. He was looking at a perfect diffraction pattern. Sharp spots, clear symmetry axes. He tilted the sample systematically and found 2-fold axes, 3-fold axes, and 5-fold axes, all at the angles predicted by icosahedral symmetry. The icosahedral point group has 6 independent 5-fold axes, 10 3-fold axes, and 15 2-fold axes. Shechtman measured them all. Every single one was where the mathematics said it should be for perfect icosahedral symmetry. This was not a smudge. This was not noise. This was not a twin artifact, because twinning produces streaking and splitting of spots, and these spots were as sharp as anything from a single crystal. This was the most forbidden symmetry in all of crystallography, captured with textbook clarity on a Tuesday morning in 1982. And nobody wanted to hear about it. I want to stop here for a moment, because the weight of what happened next tends to get lost in the retelling. Shechtman did not quietly publish his result and watch the field adjust. He endured something far more corrosive. He endured the experience of knowing he was right and being unable to make anyone believe him. That is a specific kind of loneliness that only people who have made genuinely paradigm-breaking observations can understand. You have seen something real. You have the data. You have checked the data. You have checked it again and again. And the data does not change. But the world around you has a framework that says your data is impossible. And the world chooses the framework over the evidence. Every day you walk into work knowing that the people around you think you are confused, or incompetent, or delusional. And every night you go home knowing that the diffraction pattern is still there, still sharp, still tenfold, still real. Shechtman has said in interviews that he went back to the microscope repeatedly in the days after the initial observation, re-examining the sample, looking for anything he might have missed, any artifact that could explain the pattern without invoking the impossible. He found nothing. The tenfold symmetry was robust. It appeared in multiple samples. It appeared at different tilting angles. It was not a contamination effect, because the symmetry persisted when he changed the beam conditions. It was not a surface effect, because it appeared throughout the bulk of the material. There was no escape route. The data was what it was. He was told he was wrong. He was told to read a textbook. He was told he was a disgrace. His own group leader at NBS, a man whose name Shechtman has refused to reveal publicly for over 40 years, walked into his office one morning carrying a crystallography textbook, placed it on his desk, and told him to read it so he would understand what he was talking about. Shechtman's response, which he has recounted in multiple interviews, was that he did not need to read the book. He was a professor at the Technion. His material was not in the book. A few days later, his group leader told him he wanted Shechtman out. "You are a disgrace to our group. Leave." And here is the part that should make you genuinely angry. He was right. The group leader was wrong. The textbook was wrong. Not wrong in some ambiguous interpretive way. Wrong in the most fundamental sense possible. The definition of what constitutes ordered matter, the definition that had been taught as established fact for a century, was incomplete, and it took 29 years of forced redefinition of the word crystal by the International Governing Body of Crystallography and the 2011 Nobel Prize in Chemistry before the scientific establishment formally admitted it. 29 years for a result that was correct on the day it was observed. But that is not the story I want to tell you. Or rather, it is only the first layer. Because behind Shechtman's microscope, behind his impossible diffraction pattern, behind the decades of ridicule and the eventual vindication, there is a deeper question that nobody has answered. A question that the discovery of quasicrystals opened in 1982, and that remains open today in a way that I think should unsettle you far more than the institutional politics. The question is this: how does a quasicrystal know how to grow? A regular crystal grows because each atom that arrives at the surface follows a simple local rule. It finds the lowest energy position, it bonds, and it becomes part of a pattern that repeats. The next atom does the same thing, and the next. And because the pattern is periodic, because it repeats, every atom only needs information about its immediate neighbors. Local rules produce global order. That is the magic of periodicity. It is the reason crystals exist at all, the reason snowflakes can form in mid-air without a blueprint. Local information is enough, but a quasicrystal is not periodic. Its pattern never repeats. And the mathematics of that non-repeating pattern, mathematics that Roger Penrose worked out 8 years before Shechtman ever looked through his microscope, contains a property so strange that I genuinely do not know how to square it with how we think matter assembles itself. In a Penrose tiling, which is the two-dimensional version of the pattern found in quasicrystals, placing a single tile does not just constrain the tiles next to it, it constrains tiles infinitely far away. Placing one piece of the pattern at one location forces specific pieces to appear at specific positions, thousands, millions, billions of tile widths distant. This is called the empire of a tile, and it means that the order in a quasicrystal is not local. It cannot be local. The information required to assemble the pattern correctly cannot come from the immediate neighborhood of each atom. It has to come from somewhere else. And when you ask physicists where that somewhere else is, the most honest answer you will get is a shrug, or worse, an answer that sounds like it explains things, but actually makes the problem deeper. The standard mathematical framework for understanding quasicrystals, the framework that crystallographers use every day says that a three-dimensional quasicrystal is a slice through a six-dimensional periodic crystal, a shadow projected from a higher dimension. The atoms in your three-dimensional quasicrystal sit at positions determined by a perfectly regular lattice that exists in a space you cannot access, oriented at angles defined by the golden ratio. From the perspective of six dimensions, the pattern is simple, periodic, predictable. From the perspective of three dimensions, the same pattern is aperiodic, non-repeating, forbidden. That is not a metaphor. That is the actual mathematical structure. It is called the cut and project method, formalized by Peter Kramer and Roberto Neri at Tübingen in 1984, and it is the standard model for every quasicrystal studied since. And what it implies, if you follow it to its logical conclusion, is that the atoms in a quasicrystal are following instructions from a geometry that does not exist in the space they occupy. They are assembling themselves according to a pattern that lives somewhere else, somewhere with more dimensions than the three you can measure. Remember that. I am going to come back to it, because before we can fully understand why that answer is so disturbing, you need to see how we got here. And that story starts not with Shechtman and not with a microscope, but with a mathematician who was playing with shapes on a table in the early 1970s, trying to answer a question that everyone assumed was trivial, and who accidentally discovered something that should have rewritten our understanding of order itself. A man whose discovery sat in the mathematical literature for a full decade before nature confirmed it. And even then, even after the confirmation, the significance of what he had done was ignored, because the people who should have been paying attention were too busy insisting that what he described was impossible. His name was Roger Penrose, and the thing he discovered with two simple shapes on a kitchen table was that the universe permits a kind of order that nobody had imagined could exist. Roger Penrose was born on August 8, 1931, in Colchester, Essex. His father, Lionel Penrose, was a Fellow of the Royal Society and the Galton Professor of Human Genetics at University College London, a man who did serious recreational mathematics on the side. His mother, Margaret Leeds, was a physician. His older brother, Oliver, became a Fellow of the Royal Society and a major figure in statistical mechanics. His younger brother, Jonathan, won the British Chess Championship 10 times and once defeated the reigning world champion, Mikhail Tal. His sister, Shirley, became a distinguished geneticist. This was not a normal family. This was a family where the dinner table conversation involved unsolved problems in mathematics, and the evening entertainment was chess at a level that most professionals never reach. Lionel Penrose invented the Penrose triangle, the impossible three-dimensional object that cannot exist in physical space but can be drawn on paper, and published it with Roger in the British Journal of Psychology in 1958. Escher saw their paper and used it as the basis for two of his most famous lithographs, Waterfall and Ascending and Descending. The interplay between mathematics and visual impossibility was, quite literally, a family business. Roger Penrose grew up in a household where the boundaries between the possible and the impossible were not barriers, but invitations, where the response to "that cannot exist" was not acceptance, but curiosity. That childhood shaped everything that came after, including the day he sat down with paper and scissors and asked whether a pattern could fill space without ever repeating. Penrose himself would go on to prove the first singularity theorem of general relativity, with Stephen Hawking invent twistor theory, propose a controversial theory of consciousness, and win the 2020 Nobel Prize in Physics at the age of 89. But the discovery I want to talk about is none of those. It is something smaller, something he did almost as a hobby, something that started with a question he could not stop thinking about after seeing the work of M.C. Escher at a conference in Amsterdam in 1954. The question was about tiling, specifically about whether you could tile a flat surface with a finite set of shapes that would cover the plane completely, with no gaps and no overlaps, but that would never produce a repeating pattern, an aperiodic tiling. Now, tiling might sound like a trivial problem. It might sound like the kind of thing that belongs in a puzzle book, not a physics documentary. But I need you to understand something. The question of how shapes can fill space is not a game. It is the question of how matter can organize itself. Every crystal that has ever formed, every snowflake, every grain of salt, every diamond exists because atoms can tile three-dimensional space in periodic patterns. The periodicity of crystals is not an incidental property. It is the structural backbone of solid matter. And the question of whether space can be filled without periodicity is therefore the question of whether there is a kind of solid matter that nobody has ever seen, a kind of matter that was, in 1970, not known to exist anywhere in the universe. The Escher connection matters because it shaped how Penrose thought about the problem. Escher was obsessed with tessellation, with the way shapes can interlock to fill a plane without gaps. His notebooks are full of sketches of interlocking lizards, fish, birds, shapes that tile space in clever and beautiful ways, but that are always, fundamentally, periodic. Every Escher tessellation repeats. You can pick up a section and slide it, and it maps back onto itself. Escher explored the boundaries of what periodic tiling could do, pushed it to its artistic limits, but never crossed the line into a periodicity. Penrose, after seeing Escher's work in 1954, became fascinated by the mathematical structure underneath the art, and the question he kept returning to was whether there was a form of tiling that Escher had never found, a form where the interlocking was perfect, the coverage was complete, but the repetition was absent. The seed of the idea, Penrose has said, came from a specific moment in the early 1970s. He noticed a pentagonal logo on a letterhead, a regular pentagon surrounded by 5 same-size pentagons forming a larger pentagons, and he began cutting up additional pentagons from paper and trying to fill the gaps. The triangular spaces between pentagons cannot be filled with more pentagons alone, but they can be filled with other shapes, rhombuses and partial stars and irregular pieces. And Penrose began exploring how those gap-filling shapes could be systematized. He was not trying to solve a famous problem. He was playing, cutting paper at a kitchen table, the same way his father Lionel had played with mathematical puzzles at the family dinner table decades earlier. And the playing led somewhere nobody expected. The mathematical question had a history, and the history matters because it shows how long humanity has been circling this question without understanding what it was circling. It starts with Johannes Kepler. In 1619, Kepler published Harmonices Mundi, the harmony of the world, a sprawling, eccentric masterpiece in which he tried to explain the structure of the solar system through geometry, music, and the Platonic solids. Most of the book is wrong in the way that beautiful 17th century science is wrong, full of pattern-seeking that does not survive modern scrutiny. But buried in it, in a section about the geometry of flat tilings, Kepler drew a pattern that would haunt mathematics for 4 centuries. He arranged pentagons, pentagrams, decagons, and irregular star shapes into a flat tessellation with local 5-fold symmetry. He called some of the shapes monsters because they did not fit neatly into any regular scheme. The pattern had gaps. It did not tile the plane perfectly. But Kepler had noticed, 300 years before anyone else, that 5-fold symmetry and plane filling were not as incompatible as they appeared. He had reached the edge of the problem and stopped, because the tools to go further did not exist yet. 2 centuries later, the problem took a different form. In 1961, a logician named Hao Wang at Harvard was working not with physical tiles, but with abstract square tiles whose edges were colored, and the rule was that adjacent edges had to match colors. Wang was studying the decidability of tiling, whether an algorithm could determine if a given set of tiles could cover the plane. He conjectured that the answer was yes, and that the key reason was simple. He conjectured that any set of tiles that could tile the plane could do so periodically. If Wang was right, aperiodic tilings were impossible, and the tiling problem was decidable. The conjecture felt obviously true. Periodicity seemed like the only way to cover infinite space without eventually running into contradictions. But Wang was wrong. His own student, Robert Berger, proved it in his 1964 PhD thesis, published as a monograph in the Memoirs of the American Mathematical Society in 1966, under the title The Undecidability of the Domino Problem. Berger showed that the tiling problem is formally undecidable, equivalent in computational power to the halting problem, and as a constructive byproduct of that proof, he exhibited an explicit set of tiles that could tile the plane but only aperiodically. The set contained 20,426 tiles, 20,426 distinct shapes, each one necessary, each one playing a role in forcing the pattern to never repeat. I want you to appreciate the strangeness of that number. The question was simple: can a finite set of shapes tile the plane without repeating? The answer was yes, but the first proof required a set so large that it was essentially incomprehensible. Nobody could visualize 20,000 distinct tile types assembled into a single coherent pattern. The result was correct, and it was profound, but it was also, in a practical sense, monstrous. No one could visualize what 20,000 tile types looked like assembled. No one could hold the result in their mind. And so the question immediately became a race to reduce the number, to find simpler and simpler sets that still forced aperiodicity. Berger himself simplified to 104 tiles. Raphael Robinson at Berkeley got it down to 6 in 1971, using modified squares with notches and bumps. Others found sets of 40, then 32, then smaller and smaller, each reduction feeling like progress towards some unknown minimum. And then, in 1974, Roger Penrose reduced it to 2. 2 tiles, just 2 shapes, and the plane is forced into a pattern that covers every inch of flat space, with no gaps, no overlaps, and no repetition. Ever. The compression ratio is almost absurd. From 20,000 to 2. Every step in between. Robinson's 6 tiles, the intermediate sets of 40 and 32 and 13, was considered a significant achievement. Penrose's reduction to 2 felt like reaching some kind of floor, a fundamental minimum below which the problem could not be compressed. And for nearly 50 years, that appeared to be the case. 2 tiles was the state of the art. The shapes themselves are almost comically simple. In the version known as P2, they are a kite and a dart. The kite is a quadrilateral with interior angles of 72, 72, 72, and 144 degrees. The dart is an arrowhead with angles of 36, 36, 216, and 72 degrees. The edges come in 2 lengths, and the ratio of the long edge to the short edge is the golden ratio, 1 plus the square root of 5 divided by 2, approximately 1.618. There are matching rules, little arcs or bumps along the edges that dictate which edges can sit next to which, and those matching rules are what prevent the tiles from snapping into a periodic arrangement. Without the rules, you can make a periodic pattern. With the rules, you cannot. The rules force aperiodicity. The matching rules can be visualized in several ways. Penrose originally drew them as colored arcs on each tile, 2 colors, each running from one edge to another, with the constraint that arcs of the same color must connect across shared edges. Conway and Amann found alternative ways to enforce the same constraints, using notches and tabs like jigsaw pieces, or parallel lines drawn across the tiles that must align when tiles are placed next to each other. The specific implementation does not matter. What matters is the effect. The matching rules are local. Each tile interacts only with its immediate neighbors. You cannot tell by looking at a single tile in isolation whether it is part of a periodic or aperiodic tiling. The aperiodicity is not a property of any individual tile. It is a property of the relationships between tiles. It is emergent. It arises from the local rules but manifests only at global scales. Penrose also found a second 2-tile set, called P3, consisting of a thick rhombus with angles of 72 and 108 degrees, and a thin rhombus with angles of 36 and 144 degrees. Same matching rules, same aperiodic behavior, same golden ratio saturating the structure. The P3 set is actually the version that appears most often in discussions of quasicrystals, because rhombuses are easier to draw and the connection to 3-dimensional rhombohedra, the building blocks of icosahedral quasicrystals, is more direct. What Penrose had done was compress 20,000 tiles into 2, and the pattern those 2 tiles create is one of the strangest objects in all of mathematics. A Penrose tiling has no translational symmetry. You cannot slide it in any direction and have it map back onto itself. In a periodic tiling, like a bathroom floor of square tiles, you can shift the whole pattern by 1 tile width and it looks identical. In a Penrose tiling, no such shift exists, not for any distance, not in any direction. The pattern is aperiodic in the most absolute sense. But here is the part that makes it strange. Rather than merely irregular, despite having no translational symmetry, a Penrose tiling has rotational symmetry, 5-fold and 10-fold symmetry. Specifically, the exact symmetries that the crystallographic restriction theorem says are impossible for periodic structures. And it has long-range order. Every finite patch of tiles, no matter how large, appears infinitely many times elsewhere in the tiling. If you take a photograph of any region, I can guarantee that the exact same arrangement exists somewhere else, no matter how far you have to go to find it. The pattern never repeats globally, but every local piece of it recurs infinitely. And here is where it gets worse. The ratio of kites to darts in any Penrose tiling, as the patch grows larger and larger, approaches the golden ratio. Not approximately, exactly. An irrational number hardwired into the very structure of how these 2 shapes fill space. The golden ratio does not appear because someone designed it in. It emerges inevitably from the matching rules. The shapes force it. And the golden ratio does not just appear in the tile counts. It saturates the entire structure. The spacing of Amann bars, those parallel lines that Robert Amann discovered, can be drawn across any Penrose tiling in 5 directions, follows the golden ratio. The frequencies of different vertex configurations follow the golden ratio. The ratio of the areas of the inflation and deflation stages follows the golden ratio. It is not a coincidence. It is not an aesthetic choice. It is a mathematical necessity as unavoidable as the value of pi in a circle. The golden ratio is the eigenvalue of the substitution matrix that generates the tiling, and that eigenvalue determines everything about the long-range structure of the pattern. You cannot build a Penrose tiling without the golden ratio any more than you can build a circle without pi. The number is structural. It is load-bearing. It holds the aperiodicity together. I want to make sure you understand how unusual this is. Pi appears in circles because circles are round. The connection between the number and the geometry is obvious. But the golden ratio appears in Penrose tilings for reasons that are not obvious at all. It appears because the matching rules force a particular ratio of tile frequencies, and that ratio must be irrational for the tiling to be aperiodic. And the golden ratio is the most irrational number in a precise mathematical sense, the number that is hardest to approximate by fractions, the number that sits furthest from rationality. The aperiodicity of the tiling is, in a deep sense, a manifestation of the golden ratio's extreme irrationality. The tiles avoid periodicity because the golden ratio avoids rationality. The geometry and the number theory are the same thing, seen from different angles. And there is something even stranger about the self-similarity. A Penrose tiling has inflation and deflation rules. You can take every kite in the tiling, subdivide it into 2 smaller kites and 1 smaller dart, and take every dart, subdivide it into 1 smaller kite and 1 smaller dart, and the result is a new Penrose tiling at a smaller scale. You can reverse the process too, grouping tiles into larger supertiles that form a Penrose tiling at a larger scale. This means the pattern is self-similar across all scales. Zoom in and you see the same kinds of structures. Zoom out and you see the same kinds of structures. Not the same structures, because the pattern never repeats, but the same statistical distribution, the same local configurations, the same golden ratio frequencies at every level of magnification. This self-similarity is actually the key to proving aperiodicity. If the tiling were periodic, if there was some translation that maps it onto itself, then that translation would have to commute with the inflation operation. But the inflation scales the tiling by the golden ratio, an irrational number, and no translation can commute with scaling by an irrational factor. The proof is elegant, almost silent. The golden ratio's irrationality quietly rules out periodicity at every scale simultaneously. I spent an unreasonable amount of time reading about this, and the thing that kept nagging at me was a question that Penrose himself has raised in interviews. The matching rules are local. Each tile only interacts with the tiles touching its edges, but the consequences of those rules are global. They reach across the entire infinite plane. Place 1 tile in 1 position, and you have constrained the position of tiles that are mathematically infinitely far away. The local rules contain global information, and nobody fully understands how. Penrose described his own process in characteristically understated terms. In an interview, he said he was already aware of certain non-periodic patterns of pentagons and other shapes which are, as he put it, just nice to look at. What he called the inspiration was realizing that by modifying the shapes in different sorts of ways, by putting knobs on like jigsaw pieces, you could force the pattern by local matching rules. The word he used was force, not suggest, not encourage. Force. 2 shapes with the right constraints leave the plane no choice but to organize itself into a non-repeating, golden ratio saturated, five-fold symmetric pattern of infinite complexity. The tiles do not ask the plane to be aperiodic. They demand it. And here is the detail that tends to get buried in the mathematical retelling. Penrose did not discover this in a laboratory. He did not use a computer. He sat at a table and cut shapes out of paper and moved them around by hand, the same way a child plays with blocks, the same way as it would turn out. Medieval artisans in Iran had been doing 500 years earlier, but we will get to that. In 1974, Penrose published his result in the Bulletin of the Institute of Mathematics and its Applications, Volume 10, Number 2, pages 266 to 271. It was a short paper in a small journal. The title was The Role of Aesthetics in Pure and Applied Mathematical Research. Aesthetics. He framed the entire thing as a question about beauty, and the mathematical community received it as exactly that, a beautiful curiosity, a clever piece of recreational mathematics, nice to look at, as Penrose had said, interesting in theory, but irrelevant to the physical world. The person who brought Penrose things to wide attention was Martin Gardner, the legendary recreational mathematics columnist at Scientific American. In January 1977, Gardner devoted his Mathematical Games column to Penrose's discovery, and the response from readers was enormous. Mathematicians, physicists, hobbyists, and artists began playing with the tiles, discovering new properties, exploring the strange territory that Penrose had opened. John Conway at Cambridge developed a systematic analysis of the tilings, naming the vertex configurations and establishing the deflation and inflation rules that would prove essential to understanding their structure. Robert Ammon, a remarkable amateur mathematician who worked as a mail sorter in Massachusetts, independently discovered related aperiodic tilings and introduced the Ammon bar decorations, sets of parallel lines that can be drawn across Penrose tilings in 5 directions, with spacings that follow the golden ratio. These Ammon bars would later prove crucial to connecting the tilings to real diffraction patterns. But despite all this mathematical activity, no physicist or chemist or material scientist looked at these papers and thought, this could be real. This could describe actual atoms in an actual material. The gap between the mathematics department and the chemistry department was absolute. Penrose tilings were a mathematical playground. Crystals were periodic. Those were separate worlds, and nobody saw a bridge between them, because everyone knew that real matter does not behave this way. Real atoms form periodic crystals. Real solids have translational symmetry. The 230 space groups describe every crystal that has ever existed or will ever exist. The textbooks were clear. The proof was airtight. Aperiodic tilings were a mathematical toy. They could not possibly correspond to anything in nature. That was the consensus in 1974. That was the consensus in 1975, in 1976, in 1977, in 1979, in 1980, in 1981. For nearly a decade, Penrose tilings lived in the world of pure mathematics, admired by mathematicians, ignored by physicists and chemists and material scientists, because the idea that a real material could exhibit 5-fold symmetry was not merely unlikely, it was proven impossible. And then came Alan Mackay. Alan Lindsay Mackay was born in 1926, a crystallographer at Birkbeck College in London, a student of the legendary J.D. Bernal, and a man who had spent his career thinking about the geometry of packing, specifically about icosahedral packing, the way spheres arrange themselves in clusters of 12 around one. forming 20 triangular faces, a shape with the exact five-fold symmetry that crystallography had banned. Mackay had been thinking about these forbidden geometries since the 1960s, publishing papers about what he called Mackay icosahedra, writing about five-fold symmetry when no one else took it seriously. In 1981, Mackay did something remarkable. He took Penrose's two-dimensional tiling, placed simulated atoms at every vertex, and asked what the diffraction pattern would look like. Diffraction is the gold standard of crystallography. You fire X-rays or electrons at a material, and the way the beam scatters tells you about the internal structure. Periodic crystals produce sharp spots arranged in patterns with the allowed symmetries 2, 3, 4, 6-fold. Amorphous materials produce diffuse halos. Those were supposed to be the only two options. Mackay built an optical mask of a Penrose tiling, shone light through it, and photographed the result, working with G. Harburn at Cardiff using an optical diffractometer. He produced an actual physical diffraction pattern, and it showed sharp spots, discrete points, not a halo, arranged with perfect tenfold symmetry. He published this in 1982 in Physica A, volume 114, page 609, under the title Crystallography and the Penrose Pattern, and in an earlier 1981 paper written in Russian and published in Soviet physics crystallography under the Kepler-inspired title Deneve quinquangular. On the pentagonal snowflake, he had already extended Penrose tilings to 3 dimensions using golden rhombohedra. In that paper, Mackay explicitly warned that Penrose patterns were, and I want you to hear this, an example of a pattern that might well be encountered but ignored because of preconceptions. Encountered but ignored because of preconceptions. He wrote that in 1981. Months before Shechtman looked through his microscope, a crystallographer had demonstrated that a non-periodic pattern produces sharp diffraction spots, had extended the mathematics to 3 dimensions, and had warned, in print, that the scientific community might see this in a real material and refuse to believe it. And he was right. That is exactly what happened. The preconceptions were so strong that even after Shechtman published, even after the diffraction patterns matched Mackay's predictions perfectly, the field spent years insisting the result was wrong. Mackay himself was sidelined in the telling of the story. When the Nobel Prize was awarded to Shechtman in 2011, Mackay was not mentioned. When the history of quasicrystals is told in textbooks, Mackay appears as a footnote. The man who predicted the diffraction pattern of quasicrystals before they were discovered, who extended Penrose tilings to 3 dimensions before anyone found them in nature, who warned the scientific community that they would encounter forbidden symmetry and refused to believe it, was treated as a supporting character in his own predictions' fulfillment. Mackay, Steinhardt, and Levine shared the 2010 Oliver E. Buckley Condensed Matter Physics Prize from the American Physical Society, awarded for pioneering contributions to the theory of quasicrystals, including the prediction of their diffraction pattern. That is a significant prize, but it is not the Nobel, and the asymmetry between the experimentalists' recognition and the theorists' recognition reflects something about how science values different kinds of contribution. Seeing the thing in a microscope earned the highest prize in science. Predicting the thing on paper years earlier from first principles earned a professional honor that most people outside of physics have never heard of. I am not saying Shechtman did not deserve his Nobel. He absolutely did. The courage it took to persist in the face of Pauling's opposition, to trust his own data over the most famous chemist in the world, is extraordinary. But the story of quasicrystals has multiple heroes, and the ones who predicted the result, theoretically, have been systematically underweighted in the public telling. Mackay died in 2025 at the age of 98. Steinhardt has written a book about his contributions, The Second Kind of Impossible, published in 2019 by Simon & Schuster. But the historian of science, Istvan Hargitay, and others have argued that the standard narrative underweights both Mackay's prediction and Steinhardt's theory. The story is more collaborative, more distributed, more complex than the single hero version suggests. Nobody listened. Of course nobody listened. And then came April 8th, 1982. I already told you what Shechtman saw that morning. The tenfold diffraction pattern, the icosahedral symmetry axes, the 3 question marks in his notebook. But I want to tell you what happened after, because the story of what happened after is the story of how a scientific establishment processes information that contradicts its most fundamental assumptions. And that story, it turns out, is not a story about evidence and logic and careful evaluation. It is a story about power and ego and the social enforcement of acceptable questions. Before I get to the rejection, I want to correct a misconception that I think most people carry about how crystallography works, because it matters for understanding why the establishment reacted the way it did. The misconception is that identifying a crystal structure is a matter of looking at it under a microscope and seeing the atoms. It is not. You cannot see individual atoms with an optical microscope. You cannot see them with most electron microscopes either. Not in real space. What you see is a diffraction pattern, the result of the electron beam scattering off the atomic lattice, and that diffraction pattern is a mathematical transform of the real space structure. You do not look at atoms, you look at the Fourier transform of atoms, and then you work backwards to deduce the structure. This means that a crystallographer's primary skill is not observation, it is interpretation. They see a pattern of spots, and they must infer the atomic arrangement that produced it. The pattern of spots depends on the symmetry of the lattice, and the symmetry of the lattice is constrained by the restriction theorem. So when Shechtman saw tenfold spots, the chain of reasoning that every crystallographer would automatically apply went like this. Tenfold symmetry is forbidden. Therefore, the structure cannot be a single crystal with tenfold symmetry. Therefore, the spots must be caused by something else. Twinning, multiple domains, contamination, experimental error. The conclusion that the spots were from a genuinely tenfold symmetric structure was not merely unlikely. It was logically excluded by the framework. The framework did not allow that conclusion. To accept it, you had to reject the framework, and the framework was backed by a mathematical proof. This is why the rejection was so fierce. It was not just stubbornness. It was not just ego. It was a rational response within a framework that happened to be too narrow. If you genuinely believed that fivefold symmetry was mathematically impossible in crystals, then the only rational interpretation of Shechtman's data was that it was an artifact. The problem was not that the crystallographers were irrational. The problem was that their rationality was trapped inside a set of assumptions that excluded the correct answer. And the only way out was to question the assumptions, which meant questioning the foundations of the entire field. That is a much bigger ask than most people realize. Shechtman returned to the Technion in 1983 and showed his results to a colleague named Ilan Blech. Blech took the data seriously and proposed a structural model, an icosahedral arrangement without periodicity. They wrote a paper together and submitted it to the Journal of Applied Physics. The journal rejected it, not because the data was flawed, not because the analysis was incorrect. The rejection was simply that the result was not of interest to physicists. Think about that for a moment. A paper describing the first observation of a fundamentally new form of matter a form of matter that violated a mathematical theorem that had been accepted for a century, was rejected from a physics journal because it was deemed not interesting enough. Shechtman then sent the data to John W. Kahn at the National Bureau of Standards. Kahn was a giant of material science, a theorist of phase transformations and interface thermodynamics, a member of the National Academy of Sciences. He was not a man prone to excitement over ambiguous data, but when he looked at Shechtman's diffraction patterns, he saw something that could not be dismissed. The spots were too sharp. The symmetry was too perfect. The tilting experiments were too systematic. This was not an artifact of sample preparation. This was not twinning. This was something new. Kahn's reaction tells you what a healthy scientific response looks like, in contrast to the reaction Shechtman had received from his group leader. Instead of reaching for a textbook, Kahn reached for a question. He told Shechtman, "Danny, this material is telling us something, and I challenge you to find out what it is." That sentence is the difference between a closed mind and an open one. The group leader saw data that contradicted the textbook and reached for the textbook. Kahn saw data that contradicted the textbook and reached for the data. The difference in outcome between those two responses is a Nobel Prize and a forced redefinition of crystallography. Kahn brought in the French mathematician Denis Gratius, an expert in group theory and crystallographic symmetry, who confirmed that the icosahedral symmetry was real and could not be explained by any known twinning mechanism. Together, the four of them, Shechtman, Blech, Gratius and Kahn, reshaped the manuscript into a tight 3-page communication designed to present the evidence as cleanly and undeniably as possible. Kahn, who understood the politics of publishing as well as anyone in the field, insisted on brevity. The paper needed to be so short and so clear that no referee could find room to object on technical grounds. The strategy worked. On November 12, 1984, the paper appeared in Physical Review Letters, Volume 53, Number 20, pages 1951 to 1953. Shechtman, Blech, Gratius, and Kahn. 4 authors, 3 pages, title, Metallic Phase with Long-Range Orientational Order and No Translational Symmetry. The title itself was a provocation. It stated the 2 properties that the crystallographic framework said could not coexist in the same material: long-range orientational order and no translational symmetry. The paper did not hedge. It did not speculate. It presented the data and let the contradiction speak for itself. And the field exploded. Not with acceptance, with fury. The most vocal opponent was Linus Pauling, 2-time Nobel laureate, the most famous chemist in the world, the discoverer of the alpha helix, the champion of vitamin C, the man whose textbook, The Nature of the Chemical Bond, had defined an entire discipline. Pauling was 83 years old in 1984, and he threw the full weight of his reputation against Shechtman's result. His position was that what Shechtman had observed was not a new form of matter, but a well-known artifact called multiple twinning, in which many tiny periodic crystals grow together in an arrangement that mimics forbidden symmetries. Pauling proposed increasingly elaborate models, crystals with unit cells containing over 1,000 atoms, twinned in precise orientational relationships, and he delivered his verdict in a line that would follow Shechtman for the rest of his career. There is no such thing as quasicrystals, only quasi-scientists. That is a direct quote, delivered publicly, attributed by Shechtman himself in multiple interviews. Pauling did not just disagree with the data. He attacked the competence of the person who collected it. And because Pauling was Pauling, because he was a 2-time Nobel laureate and the most visible chemist on the planet, people listened, not to the data, To the authority, I need to pause here because the institutional dynamics of what happened between 1984 and 1994 are not incidental color. They are load-bearing. They are the reason you were never taught this in school. They are the reason the word quasicrystal does not appear in most physics textbooks. Even today, even after the Nobel Prize, the mechanism of suppression was not a conspiracy. It was something more insidious. It was the social enforcement of acceptable questions. It was career incentives, textbook committees, grant panels, all operating on the implicit assumption that certain questions had been answered in the 1890s, and that anyone reopening them was either confused or a crank. Shechtman described it himself on the day his Nobel Prize was announced, October 5th, 2011, in a press release from Iowa State University. His words were these: "For a long time it was me against the world. I was a subject of ridicule and lectures about the basics of crystallography. The leader of the opposition to my findings was the two-time Nobel laureate Linus Pauling, the idol of the American Chemical Society, and one of the most famous scientists in the world. For years, till his last day, he fought against quasi-periodicity in crystals. He was wrong, and after a while, I enjoyed every moment of this scientific battle, knowing that he was wrong. Till his last day. Pauling died on August 19th, 1994. 10 years of opposition. He never accepted quasicrystals. He went to his grave insisting that what Shechtman had found was twinned periodic crystals. And by 1994, the evidence against Pauling's position was overwhelming. In 1987, and Pang Tsai at Tohoku University had synthesized stable quasicrystals of aluminum, copper, and iron, large enough for X-ray diffraction, with no twin boundaries visible under any microscopy. The twinning model was dead, but Pauling would not let go, because admitting Shechtman was right meant admitting that a fundamental assumption of crystallography was wrong. And for a man who had built his career on the foundations of structural chemistry, that was unacceptable. The Nobel Prize citation, when it finally came 29 years after the discovery, reads simply, "For the discovery of quasicrystals." The Royal Swedish Academy of Sciences wrote that his discovery was extremely controversial, but that his work eventually forced scientists to reconsider their conception of the very nature of matter. Shechtman received the prize alone, which is unusual for a science Nobel and reflects the fact that he was, in the end, the person who saw the thing, believed the thing, and refused to be told the thing did not exist. Kahn had died in 2016. Blesch did not share the prize. Steinhardt and Levine, who provided the theoretical framework, did not share the prize. The Nobel Committee chose to honor the act of observation and the act of intellectual courage, which in this case were the same act, in a detail that captures something essential about the man. Shechtman ran for president of Israel. In 2014, he received 1 vote in the Knesset. The Israeli press called him the quasi-president. He laughed about it. This is the pattern. First, it was impossible. Then, when someone did it, it was an artifact. Then, when the artifact explanation failed, it was trivial. The one thing it could never be was important. And that pattern did not end with Pauling's death. I want to give you one more piece of the Pauling story, because it illustrates something essential about how scientific authority works. Pauling's twinning model was not stupid. It was wrong, but it was not stupid. The idea that many small periodic crystals could grow together in specific orientational relationships to produce a diffraction pattern that mimics forbidden symmetries is a real phenomenon. It happens. It is called multiple twinning. and it is a known source of confusion in crystallography. What Pauling was proposing was physically possible in principle, but it was not what was happening in practice, and the evidence against it accumulated rapidly. If Shechtman's samples were multiply-twinned, you would expect to see twin boundaries, thin interfaces where one crystal orientation meets another, visible under high-resolution electron microscopy. No twin boundaries were found. You would expect the diffraction spots to be slightly split or streaked, because the many tiny twins would be imperfectly aligned. The spots were sharp. You would expect the phenomenon to be sample-dependent, appearing in some preparations and not others. It appeared in every aluminum manganese sample of the right composition, regardless of how it was prepared. And critically, you would expect the twinning model to predict the diffraction pattern quantitatively, with specific spot positions and intensities. It did not. The quasi-crystal model did. Pauling responded to each piece of contrary evidence by making his twinning model more complex. His unit cells grew. His twin orientational relationships multiplied. By the late 1980s, he was proposing structures with over 1,000 atoms in the unit cell and 20 different twin orientations, an edifice of such baroque complexity that it had lost all the elegance that was supposed to be its advantage over the quasi-crystal interpretation. He was a great scientist doing bad science, and the reason was not incompetence. The reason was that the alternative, accepting that the definition of a crystal was wrong, was psychologically intolerable for a man who had spent 60 years building his career on the foundations of structural chemistry. I think there is a lesson there that goes beyond Pauling and beyond crystallography. The capacity of a brilliant person to be wrong increases, not decreases, with the amount they have invested in being right. Pauling's eminence was not a safeguard against error. It was the cause of it. His authority made it harder for him to update his beliefs and harder for the field to override his judgment than it would have been for a lesser figure. The social structure of science, which grants disproportionate weight to the opinions of Nobel laureates, became a mechanism for propagating an incorrect conclusion. And the people who suffered were not other Nobel laureates. They were junior scientists, graduate students, postdocs, people who saw quasicrystals in their own experiments and were afraid to publish because Linus Pauling had said they were impossible. That is not ancient history. Shechtman received his Nobel in 2011. The last textbook that defined crystals as periodic was published more recently than that. The institutional inertia is still dissipating. But if you want a measure of how completely the field eventually absorbed Penrose's mathematics, consider this. In 1997, Roger Penrose discovered that his tiling pattern had been embossed on toilet paper. Kimberly-Clark, the company that makes Kleenex, had launched a product called Kleenex Quilted in the United Kingdom, and the quilting pattern on the tissue was, unmistakably, a Penrose tiling, specifically the P3 thick and thin rhombus version. The commercial advantage was real. Because the pattern is aperiodic, it does not bunch or stack the way a periodic pattern does when wound onto a roll. The mathematical property that makes Penrose tilings interesting to mathematicians also makes them useful for toilet paper manufacturing. Penrose, who had been awarded a US patent on his tiling in 1979 through a company called Pentaplex Limited, was not amused. He learned about the product when his wife brought a roll home from a supermarket. Pentaplex Limited sued Kimberly-Clark for copyright infringement, and the company's statement to the press read, "And I am not making this up. When it comes to the population of Great Britain being invited to wipe their bottoms on what appears to be the work of a knight of the realm without his permission, then a last stand must be made." Kimberly-Clark withdrew the product, 4 rolls are now permanently archived in the Science Museum in London. I tell you that story because it is funny, but also because it is revealing. By 1997, Penrose's patent had moved from pure mathematics to industrial application without passing through the stage of being taken seriously as physics. The tiles were beautiful. The tiles were useful. But the idea that the tiles described something real about the structure of matter was still, in many quarters, treated as an exotic curiosity rather than a fundamental discovery about the nature of order. The institution absorbed the product. It had not yet absorbed the implications. But something else was happening in parallel with the controversy, something I have not mentioned yet, and it is the part of this story that I think has the deepest implications. Because while Shechtman was fighting for the legitimacy of his discovery, a theoretical physicist at the University of Pennsylvania had already figured out exactly what quasicrystals were, and the answer involved mathematics that should not apply to anything in the real world. His name was Paul Steinhardt, and the theory he developed with his graduate student Dov Levine would reveal that the connection between Penrose's paper tiles and Shechtman's impossible crystal was not a coincidence. It was inevitable, because the mathematics of non-repeating patterns is not a game. It is the description of how matter can organize itself when it has access to information from beyond the dimensions you can see. Steinhardt had been working on icosahedral symmetry since 1981, independently of Mackay, motivated directly by Penrose tilings. He had been asking the question that nobody else in physics was asking. What if atoms could arrange themselves in non-periodic structures with the symmetry of an icosahedron? What would such a structure look like to an X-ray beam? What diffraction pattern would it produce? He and Levine had computed the answers theoretically, predicted the positions and intensities of the diffraction spots, and they were sitting on a prediction for which no experimental confirmation existed. When a colleague at the University of Pennsylvania showed Steinhardt a preprint of Shechtman's Physical Review Letters paper in the autumn of 1984, the moment was electric. Steinhardt has described it in interviews and in his book. He leapt up in the air. The computed diffraction patterns that he and Levine had generated from their theoretical quasicrystal models matched Shechtman's experimental data by eye. The spot positions matched, the symmetry axes matched, the intensity distributions matched. What Steinhardt had predicted from pure theory, Shechtman had found in an actual material. The mathematics and the experiment converged independently from different starting points on the same impossible structure. Within 6 weeks, working at a speed that reflects the intensity of the moment, Levine and Steinhardt published their own paper in Physical Review Letters, Volume 53, Number 26, December 24th, 1984, pages 2477 to 2480, with the title Quasicrystals, a new class of ordered structures. It was this paper that coined the term quasicrystal, a shorthand for quasi-periodic crystal, borrowing from the Danish mathematician Harald Bohr's 1924 theory of quasi-periodic functions. The name stuck. It is the name used today. And here is what they proposed. A quasicrystal is not disordered. It is not random. It is not somewhere between crystalline and amorphous. It is a new category entirely. It has long-range order, meaning sharp Bragg peaks in diffraction, but no translational periodicity. It has rotational symmetries that are forbidden in periodic structures, 5-fold, 10-fold, 12-fold, because those symmetries are only forbidden if you insist on periodicity. Abandon periodicity and the restriction theorem does not apply. The theorem does not say five-fold symmetry is impossible in matter. It says five-fold symmetry is impossible in periodic matter. That distinction, which sounds like splitting hairs, is actually the entire point. And the model Steinhardt and Levine proposed for how these structures work was the cut and project method, formalized simultaneously by Peter Kramer and Roberto Neri at the University of Tübingen. Let me walk you through this because I think it is one of the most beautiful ideas in all of physics, and I think it has implications that extend far beyond crystallography. Imagine a two-dimensional creature living on a flat plane. This creature can perceive 2 dimensions, but not 3. Now imagine that above this flat plane, extending upward into the 3rd dimension that the creature cannot perceive, there is a perfectly regular 3-dimensional lattice, like the scaffolding on a building, with atoms at every intersection point. The creature cannot see this lattice. It does not know it exists. But if you slice through that 3-dimensional lattice with the creature's 2-dimensional plane, some of the lattice points will land on or near the plane, and the creature will see those points scattered across its flat world. If you orient the slice perfectly, at a rational angle to the lattice axes, the points the creature sees will form a periodic 2-dimensional pattern, an ordinary crystal from the creature's perspective, regular, repeating, explainable, with 2-dimensional mathematics. But if you tilt the slice to an irrational angle, something remarkable happens. The points the creature sees will still be ordered. They will still produce sharp diffraction spots, but they will not be periodic. They will form a quasi-crystalline pattern with rotational symmetries that the creature's 2-dimensional restriction theorem says are impossible. The creature will see forbidden symmetry, and it will be real, mathematically provable, a direct consequence of the geometry of a space the creature cannot access. Now scale that up. Our 3-dimensional quasi-crystal is the creature. The 6-dimensional periodic lattice is the scaffolding. The irrational angle of the slice is defined by the golden ratio, and the atom positions we measure in 3 dimensions are the lattice points that fall on or near our 3-dimensional hyperplane. From the perspective of 6 dimensions, the pattern is periodic. It repeats. It has translational symmetry. It is a perfectly ordinary crystal. But from the perspective of the 3-dimensional slice, the pattern is aperiodic. It never repeats. And the rotational symmetry of the 3-dimensional projection is 5-fold, the exact symmetry that the crystallographic restriction theorem bans. I need you to sit with that for a moment. The most accurate mathematical description of a quasicrystal, the model that correctly predicts diffraction patterns, atomic positions, and physical properties, says that your 3-dimensional quasicrystal is a shadow, a projection, a slice of a perfectly ordered structure that exists in a space with more dimensions than the 3 you inhabit. The atoms in the quasicrystal are sitting at positions determined by a lattice you cannot access. They are following a pattern that lives somewhere else. And this is not a metaphor. This is not a heuristic. This is the standard mathematical framework used by working crystallographers every day. Superspace groups, the generalization of the 230 space groups that describes quasicrystals, are defined in higher dimensional spaces. The calculations are done in 6 dimensions. The answers are projected down to 3. The method works. It predicts correct diffraction patterns. It predicts correct atomic positions. It is the accepted model, but nobody talks about what it means. I want to come back to the empire problem now, because I promised you we would return to it, and because it connects directly to the cut and project framework in a way that makes the whole picture more unsettling, not less. In a Penrose tiling, every tile has an empire. Place a single kite at a specific position and orientation, and you have determined with mathematical certainty that specific other tiles must exist at specific positions arbitrarily far away. Not probably, not with high likelihood, with absolute logical necessity. The matching rules that prevent periodicity also create these infinite range correlations. A decision here constrains reality there, where they can be as far away as you like. In a real quasicrystal, this translates to a physical puzzle that nobody has solved. When an aluminum atom arrives at the growing surface of a quasicrystal, it needs to find the right position. In a periodic crystal, this is easy. The atom looks at its neighbors, finds the lowest energy site, and sits down. Local rules suffice. But in a quasicrystal, the correct position of each atom depends on the positions of atoms that may be thousands of unit cells away. Atoms, the incoming atom, has no way of sensing. The pattern is non-local. The information required to grow the pattern correctly cannot be contained in the immediate environment of any single atom. So how does the crystal grow? This is not a rhetorical question. This is the central unsolved problem of quasicrystal physics, and it has been open for over 40 years. Every attempt to answer it runs into the same wall, and that wall is the non-locality of the pattern. Let me make the problem more concrete. Imagine you are building a Penrose tiling by hand, one tile at a time, starting from the center and working outward. You place your first kite. Fine, you attach a few more tiles around it, following the matching rules, and everything seems to work. The rules tell you which edges can touch which, and at any given step, there are usually only a few legal options. It feels local, it feels manageable. But as the tiling grows, you start to encounter a problem. The matching rules are local, but they are not complete. There are situations where multiple tiles are locally legal, where the matching rules allow more than one option, but only one of those options is globally correct. If you pick the wrong one, you will eventually reach a configuration where no tile fits. The tiling is stuck. It cannot grow further without ripping out tiles and starting over. In a periodic crystal, this cannot happen. Every locally legal choice is also globally legal, because the pattern repeats and there is no future constraint that could conflict with a present choice. But in a Penrose tiling, the future constrains the present. A choice you make now can create a contradiction 1,000 tiles later. And the only way to avoid that contradiction is to know in advance information about the pattern at a distance you have not reached yet. This is the empire problem translated into a growth algorithm. And it means that building a perfect Penrose tiling from local rules alone is, as far as anyone knows, impossible. You either need global information, some kind of long-range coordination, or you need to accept imperfections, defects in the tiling that accumulate as it grows. One proposal, put forward by George Onoda, Paul Steinhardt, David DiVincenzo, and Joshua Sokolow in a 1988 Physical Review Letters paper, suggests that local growth rules can produce perfect quasicrystals if the rules are sophisticated enough, involving not just nearest neighbors, but next nearest neighbors and specific overlap conditions. Sokolow and Steinhardt showed in 1986 that if you allow atoms to interact with neighbors up to a certain distance, and if the interaction rules are carefully chosen, the growth can proceed without errors. But the required interaction range is longer than for any periodic crystal, and the rules are remarkably specific. The atoms need to know not just about the tiles touching them, but about tiles several layers out. Whether real interatomic forces have the right form to implement these rules is an open question. Another school of thought, championed by Christopher Henley at Cornell and Victor Elser at Cornell, argues that real quasicrystals are not perfect Penrose tilings at all. They are random tilings, disordered versions of quasi-crystalline order, stabilized by entropy at high temperature. In this view, the atoms do not need to know about distant atoms because the structure tolerates errors. It is close enough to a perfect quasicrystal to produce sharp diffraction spots, but it is not exact. The entropy of the random tiling, the number of distinct ways the tiles can be arranged while maintaining approximate quasicrystalline order, provides a thermodynamic driving force that stabilizes the structure at high temperature. When the material is cooled, the structure freezes in place, imperfections and all. This is an elegant proposal, and it may be correct for some quasicrystals, but it has a problem. Some quasicrystals are astonishingly well ordered, and Pang-size, stable aluminum copper-iron quasicrystals, the ones that killed Pauling's twinning model, have diffraction peaks as sharp as any periodic crystal. The order is not approximate, it is precise, and precision in a random tilling model requires explanation. If the structure is entropy stabilized, it should have a characteristic amount of disorder. Size quasicrystals appear to have less disorder than the model predicts. They are too perfect. And a third possibility, the one that keeps me up at night, is that the cut-and project framework is not just a calculational tool, that the higher dimensional periodic lattice is not an abstraction, but a description of something real about the physics, that the atoms in a quasicrystal really are following a pattern from a higher dimensional space, and the reason local rules seem insufficient is that the rules are not local at all. They are operating in a space with more dimensions than the ones we measure. Penrose himself has gestured at something like this. In interviews about quasicrystals, he has said that they cannot be produced simply with local rules, that there has to be some subtle kind of production. Steinhardt has admitted that the mathematical techniques developed for periodic crystals do not work on quasicrystals, that we cannot predict their properties as well as we can for ordinary crystals. These are not fringe figures speculating. These are the people who built the field, and they are telling you that the deepest question about quasicrystals remains unanswered. How does a non-periodic pattern assemble itself from local interactions? How does an atom know where to go when the pattern it is joining requires information from beyond its immediate surroundings? How does a crystal follow a blueprint that exists in 6 dimensions when it is being built in 3? Those questions are not rhetorical. They are open research problems. They have been open since 1984. And the reason you have never heard them discussed is not that they were answered. It is that they were never asked publicly, because asking them requires you to say something uncomfortable about the nature of order in the physical world. It requires you to say that there may be kinds of structure in matter that our 3-dimensional physics is not equipped to explain. And here is where the story takes a turn that I did not expect when I started researching this. I assumed this was a 20th century story. Penrose in 1974, Shechtman in 1982, the Nobel in 2011. A clean arc of discovery, rejection, and vindication. But the more I dug, the more I realized the timeline was wrong, because humans did not discover non-periodic patterns in 1974. Humans discovered non-periodic patterns at least 5 centuries earlier, and they did it not with mathematics, not with electron microscopes, not with 6-dimensional projections, but with tiles on a wall. In 2007, a Harvard graduate student named Peter Liu and Princeton physicist Paul Steinhardt, the same Steinhardt, published a paper in Science, volume 315, pages 1106 to 1110, titled Decagonal and Quasi-Crystalline Tillings in Medieval Islamic Architecture. They had analyzed the tilework of the Darby-Imam shrine in Isfahan, Iran, built in 1453. And what they found was that the artisans who decorated this shrine had used a set of 5 shapes: decagons, pentagons, elongated hexagons, bautis, and rhombuses, which they called Jurith tiles, to construct a pattern with near-perfect 10-fold symmetry and a self-similar structure across 2 distinct scales. Liu and Steinhardt mapped 3,700 individual tiles on the shrine's spandrel. They found 11 small defects, 11 out of 3,700. The rest was a quasi-crystalline pattern, mathematically equivalent to a Penrose tiling, executed by hand in glazed ceramic on a mosque wall, 521 years before Roger Penrose published his paper. I want to stop here because I think the significance of this gets lost if you move past it too quickly. The 11 defects in 3,700 tiles represents an error rate of 0.3%. For a hand-assembled pattern, using no mathematical formalism, no coordinate system, no knowledge of aperiodicity as a concept, that precision is staggering. The artisans were not placing tiles randomly and hoping for the best. They had a system. The Garish tiles themselves, with their specific shapes and edge decorations, function as a set of matching rules, just like Penrose's arcs and bumps. The strapwork pattern that decorates each tile connects seamlessly across edges only when the tiles are placed correctly. The beauty of the pattern was the enforcement mechanism. If a tile was in the wrong position, the strapwork would not align and the artisan would see the error and correct it. Aesthetics was doing the work of mathematics. And the self-similarity that Liu and Steinhardt identified adds another layer. The shrine's tilework operates at 2 distinct scales. At the larger scale, the Meteorite tiles form a decagonal pattern. At the smaller scale, each large tile is subdivided into smaller Meteorite tiles that form a similar decagonal pattern at a finer resolution. This is deflation, the same operation that Penrose used to prove the aperiodicity of his tilings. The artisans in Isfahan had discovered substitution rules, the mathematical engine of aperiodic order, through purely visual and geometric reasoning, 5 centuries before anyone in the Western tradition formalized the concept. Earlier proto-quasicrystalline patterns appear on the Gunbad-i-Kabud tomb, tower in Maragheh, Iran, built in 1197, and a scroll now held in the Topkapi Palace in Istanbul, dating to around 1500, contains templates for Garish tile patterns that are essentially instruction manuals. The tradition was old, it was deep, it was sophisticated, and it was invisible to Western science until 2007. In 1453, artisans in Isfahan, working without the concept of a lattice, without the crystallographic restriction theorem, without even the vocabulary of periodicity and aperiodicity, constructed a tiling that Western mathematics would not describe until 1974, that Western crystallography would not recognize in nature until 1982, and that Western science would not formally accept until 1992. They did it with hand-cut tiles and a tradition of geometric pattern making that stretched back centuries. The Gunbad-i-Kabud tomb tower in Maragheh, Iran, built in 1197, already shows proto-quasi-crystalline patterns. A scroll in the Topkapi Palace in Istanbul, dating to around 1500, contains Garish tile templates that are essentially instruction manuals for constructing these patterns. The Danish crystallographer Emil Makovicki had noticed Penrose-like features in Islamic architecture as early as 1992, but it took Liu and Steinhardt's systematic analysis to show that this was not a coincidence. The Islamic artisans had developed, through centuries of accumulated craft knowledge, a working understanding of non-periodic order. They had found their way to the golden ratio, to fivefold symmetry, to self-similar inflation, without any of the mathematical framework that Penrose used. They had done it by looking at what was beautiful, and nobody in Western science had noticed. For decades after Penrose's paper, for decades after Shechtman's discovery, Western scientists discussed quasicrystals as if they were an entirely modern phenomenon, as if the idea of non-periodic order was born in the 20th century. The shrines were right there. The patterns were right there. And the people who should have been looking at them were too focused on their own frameworks to see what had been sitting in Isfahan for half a millennium. That is the institutional pattern again, not conspiracy. Something worse, a failure of imagination so complete that an entire civilization's mathematical achievement was invisible because it came in the wrong form, from the wrong culture, in the wrong century. But even the Islamic artisans, for all their brilliance, were working in 2 dimensions. They were making patterns on walls. They were not making matter. The question of whether nature itself could produce quasi-crystalline order, whether the universe would choose to arrange atoms in this forbidden geometry without any human intervention, remained open until much later than you would expect. Because after Shechtman's 1982 discovery, after the 1984 papers, after the Nobel Prize, after over 100 different quasi-crystal compositions were synthesized in laboratories around the world, there was still a quiet asterisk on the whole field. Every known quasi-crystal had been made by humans. Rapidly cooled alloys, carefully controlled compositions, laboratory conditions. The implicit assumption, rarely stated but widely held, was that quasi-crystals were a laboratory curiosity, an interesting metastable phase that required human intervention to produce. Nature, left to its own devices, made periodic crystals. The forbidden symmetries were a trick we had to force. And then Paul Steinhardt, the same man who had coined the word quasi-crystal, who had predicted their diffraction patterns, who had shown that Islamic artisans had been making them for centuries, decided to find one that nature had made on its own, without human help, without any intervention at all. The search took him over a decade. It took him across continents. It took him to a museum in Florence, to mineral dealers in Amsterdam, to a Russian mining region so remote that it took 10 days of travel from the nearest city. And what he found at the end of that search was something that nobody expected. He found quasi-crystals in a meteorite, a 4.5 billion-year-old rock from space. The search began in 2001 when Steinhardt and the Italian mineralogist Luca Bindi of the University of Florence started a systematic hunt through museum mineral collections. The idea was simple, but the execution was grueling. If quasi-crystals can form in a laboratory, perhaps they can also form in nature, under extreme conditions of temperature and pressure. And if they had formed in nature, they might be sitting unrecognized in some mineralogist's collection, catalogued as something ordinary, their forbidden symmetry unexamined because nobody had thought to look. For years, they found nothing. They examined thousands of samples. They ran diffraction tests on minerals from all over the world. The problem was not just finding a quasi-crystal. It was recognizing. 1. Before Shechtman, any mineralogist who saw a diffraction pattern with 5-fold symmetry in a natural sample would have assumed it was an error, a twinned crystal, a contaminated sample. The very thing they were looking for was the thing the field had been trained to dismiss. In 2007, Bindi came across a specimen in the Florence Museum of Natural History, catalogue number 46407, G, labeled Quasicrystals, a mineral of aluminum and copper. The specimen had been acquired by the museum in 1990 through unclear channels, apparently originating from the Koryak Mountains in the Kamchatka region of far eastern Russia. It was small, unremarkable, the kind of sample that sits in a museum drawer for decades without anyone paying attention to it. But Bindi found a tiny grain within the specimen, about 3 millimeters across, that contained an unusual phase. They prepared thin sections, put them in the electron microscope, and the diffraction pattern appeared. Icosahedral symmetry, sharp spots, forbidden axes. The composition was aluminum 63, copper 24, iron 13. It was a quasicrystal. And it was natural. They published the result in Science in June 2009. Bindi, Steinhardt, Yao, and Liu. Natural quasicrystals. The mineral was formally accepted by the International Mineralogical Association under the name icosahedrite. But the question of where it came from, how it formed, what conditions could produce a natural quasicrystal, required knowing the history of the rock that contained it. And oxygen isotope analysis revealed something extraordinary. The ratios of oxygen-16 to oxygen-17 were inconsistent with any terrestrial formation process. They were wildly different from any ratio found in Earth rocks. They matched, precisely, the ratios found in a specific class of extraterrestrial material, carbonaceous chondrite meteorites, CV3 type. The grain was not from Earth. It had formed in space, approximately 4.57 billion years ago, in the earliest days of the solar system. I need to pause here because I want you to feel the weight of that. The first natural quasicrystal ever identified by human science did not come from a mine or a volcano or a geological formation anywhere on this planet. It came from a rock that had been drifting through space for longer than the Earth has existed. It formed in conditions so violent, collisions between protoplanetary bodies in the accretion disk of the young sun, that the temperatures exceeded 1,200 degrees Celsius and the pressures topped 5 gigapascals, the equivalent of 50,000 atmospheres. And in those hellish conditions, atoms of aluminum and copper and iron, without any laboratory, without any scientist, without any intention at all, assembled themselves into a pattern with icosahedral symmetry, a pattern that never repeats, a pattern that the textbooks said was impossible. But Steinhardt was not done. He wanted to find more material from the same source, to confirm the result independently, to understand the formation conditions in detail. And that meant going to the Koryak Mountains himself. From July 20th to August 7th, 2011, Steinhardt led a 10-person expedition of American, Russian, and Italian scientists to one of the most remote regions on Earth. The Koryak Mountains are in the far northeast of Kamchatka, accessible only by helicopter from the nearest settlement, which is itself accessible only by helicopter from the nearest city. The team camped along the banks of a small stream called the Listvenitovi, panning for meteorite fragments, the way gold prospectors pan for nuggets, sifting through mud and gravel and freezing water for tiny grains of extraterrestrial metal. They were accompanied by a bear guard because the region is dense with Kamchatka brown bears. Steinhardt, a theoretical physicist from Princeton, was sifting stream sediment in a Russian wilderness, looking for microscopic pieces of a 4.5 billion year old asteroid. If you had told his colleagues in 1984, when he published his first quasicrystal paper, that this is where the research would lead, they would not have believed you. They found what they were looking for: fresh fragments of the Quasicrystal meteorite, confirmed by the same oxygen isotope ratios. And in those fragments over the next several years, they identified not one, but 3 natural quasicrystal minerals: icosahedrite, confirmed in the field samples; decagonite, aluminum-71 nickel, 24 iron 5, reported in scientific reports in 2015, the first natural quasicrystal with decagonal rather than icosahedral symmetry; and a second icosahedral phase, aluminum-62 copper 31 iron 7, published in scientific reports in December 2016, which was remarkable for a reason that deserves its own paragraph. That third quasicrystal, the one from 2016, was the first quasicrystal composition ever found in nature before being synthesized in a laboratory. Every other quasicrystal in history, all 100+ of them, had been made by humans first and found in nature second, or not found in nature at all. This one was the other way around. Nature made it first. In the violence of an asteroid impact, 4.5 billion years ago, in a part of the solar system that was still forming, atoms found their way to a quasi-crystalline arrangement that no human had ever produced. The universe was making quasicrystals before the Earth existed. And the Quasicrystal meteorite was not the end of the story. In 2021, Bindi and colleagues published a paper in the Proceedings of the National Academy of Sciences reporting the discovery of an icosahedral quasicrystal in trinitite, the glassy material formed when the first atomic bomb was detonated at the Trinity test site in New Mexico on July 16, 1945. The quasicrystal formed in the fireball 29 kilotons of explosive force, temperatures exceeding 8,000 degrees Celsius, and the sand beneath the bomb fused into a new kind of glass, containing a phase with 5-fold symmetry that had never been seen before in any laboratory. In 2023, they found another one, this time in a fulgurite from Nebraska, a tube of fused sand created when lightning strikes the ground. The strike lasted a fraction of a second. The temperatures reached 30,000 degrees Celsius, and in that brief, violent moment, a dodecagonal quasicrystal formed, 12-fold symmetry, in sand, made by lightning. Do you see what is happening here? Quasicrystals form in the most extreme conditions nature can produce: asteroid impacts, nuclear explosions, lightning strikes. These are not gentle equilibrium processes. These are the most violent events in the natural world. Conditions where normal rules break down, where the usual slow process of crystal growth is replaced by instantaneous, catastrophic solidification. And in those conditions, atoms choose quasicrystalline order, not periodic order, not amorphous disorder. The forbidden symmetry, as if the extreme conditions strip away whatever barrier normally prevents quasicrystals from forming, and the atoms revert to some more fundamental arrangement that periodicity was only an approximation of. I am speculating now. That last sentence goes beyond the published evidence, but the pattern is striking, and I do not think it is a coincidence that the natural quasicrystals keep appearing in the most violent environments the universe can offer. And still we have not reached the bottom, because there is a question embedded in the meteorite discovery that almost nobody has discussed publicly. And it is the question that connects everything in this story, from Penrose's paper tiles, to Shechtman's microscope, to the Darbai Imam shrine, to the Koryak Mountains. The question is about what order means, about whether the concept of order that Western science has been using for 400 years is fundamentally too narrow. The old definition of a crystal, the periodic one, carried an implicit assumption that nobody examined because it felt too obvious to question. The assumption was that order requires repetition. That to be organized, a structure must be predictable through translation. That regularity means periodicity. This was not stated as a hypothesis. It was treated as a tautology. Order is repetition. Randomness is the absence of repetition. Those were the only two categories. And quasicrystals destroyed that binary. They showed that there is a third option. A structure can be ordered without repeating. It can have sharp diffraction peaks without having a unit cell. It can have more rotational symmetry than any periodic crystal, not less. The aperiodic pattern is not a degraded version of crystalline order. It is a richer version, a version with more symmetry, more internal structure, more mathematical depth than any periodic crystal can achieve. Ron Lifshitz of Tel Aviv University put it as clearly as anyone. The order is as good as you find in periodic crystals, but it is not based on periodicity. It is based on quasi-periodicity, which is a different mathematical notion, of order. That is what Shechtman found in 1982. Not a new mineral, not a new alloy, a new kind of order, one that the human race had been looking at for centuries in the tiles of Isfahan and had failed to recognize because the definition of order was too small. The 1992 redefinition by the International Union of Crystallography reflects this. They replaced the old definition with a new one. A crystal is any solid having an essentially discrete diffraction pattern. That is it. No mention of periodicity, no mention of translational symmetry, no mention of unit cells. The operational criterion is simply Bragg peaks. If your material produces sharp spots when you fire X-rays through it, it is a crystal. And the IUCR explicitly acknowledged that this definition was provisional. They wrote that it was interim, because we do not yet have a complete mathematical characterization of all the atomic arrangements capable of producing discrete diffraction. In other words, we do not know the full extent of what order looks like. We have not finished cataloging the kinds of structure that matter can adopt. The periodic crystals that filled the textbooks were not the whole story. They were a subset, and the size of the set they are a subset of is still unknown. David Van Aken of Missouri University of Science and Technology captured the magnitude of what happened in a sentence that I think is worth repeating. He said, "Crystallography was considered a closed science. There was nothing more to learn. His discovery took a settled science and turned it upside down. A closed science." Think about how rarely that phrase applies in the history of knowledge. Crystallography was not a field with open questions and competing hypotheses. It was a field that believed it was finished. The 230 space groups had been classified. The restriction theorem had been proved. The textbooks had been written. The exam questions had been standardized. And then one man with an electron microscope showed that the entire framework was a special case. The institutional reckoning was slow and painful. Between 1984 and 1992, the field was split. Some crystallographers embraced quasicrystals immediately, seeing them as a gift, a new frontier in a science that had seemed complete. Others resisted, sometimes fiercely, insisting that the observed phenomena could be explained within the existing framework. Papers were published arguing for and against. Conferences became contentious. Careers were shaped by which side a young researcher chose. By the late 1980s, the evidence was overwhelming. Over 100 distinct quasi-crystal compositions had been synthesized. Stable quasi-crystals, not just the rapidly cooled metastable phases that Shechtman had first observed, were produced in laboratories around the world. And Pang Tai's thermodynamically stable aluminum copper iron quasicrystals could be grown as millimeter-sized single grains, large enough for single crystal X-ray diffraction, displaying icosahedral symmetry without a trace of twinning. 8-fold quasicrystals were found. 12-fold quasicrystals were found. The phenomenon was not a curiosity. It was a category. And then, in 1992, the IUCR changed the definition. Not because it wanted to. Because it had no choice. The evidence had outgrown the framework, and the framework had to be rebuilt. As of 2025, by the most careful count available, published by Yuryu and colleagues in Scientific Data in 2024, and confirmed by Takakura and colleagues in the IUCR Journal in 2025. Over 100 thermodynamically stable quasi-crystal compounds are known. They are, as the 2025 paper puts it, recognized as universal phases of matter. Universal, not exotic, not anomalous. Universal. That is where the science stands right now, as of 2026. And it is where the implications become genuinely personal. Because the question of what constitutes order is not an abstract mathematical curiosity. It is a question about the deep structure of everything. Every model in physics, from solid-state physics to quantum field theory to cosmology, relies on assumptions about what kinds of order are possible. If those assumptions are too narrow, if we have been using a definition of structure that excludes real phenomena, then the models built on that definition are also too narrow. And the history of quasicrystals suggests, with uncomfortable clarity, that this is exactly what happened. For 100 years, we defined order too narrowly. We missed a category. And we missed it not because the evidence was hidden, but because we were not looking. And the missed category is not small. Think about what periodicity gives us. It gives us band theory, the framework that explains how electrons move through solids, which is the foundation of all semiconductor physics, which is the foundation of every electronic device you own. It gives us phonon theory, the framework that describes heat conduction and sound propagation in crystals. It gives us Bloch's theorem, which says that the wave function of an electron in a periodic potential has a specific mathematical form. And that form is the basis of everything we know about electrical conductivity, optical properties, magnetic properties, and thermal properties of crystalline materials. All of that, every piece of it, assumes periodicity, assumes that the atoms repeat, assumes that there is a unit cell. What happens to band theory in a quasicrystal? What happens to Bloch's theorem when there is no unit cell? The honest answer is that we do not fully know. We have approximate methods. We have numerical simulations. We have the superspace formalism, which restores periodicity by going to higher dimensions. But the intuitive physical understanding that exists for periodic crystals, the understanding that lets a physicist look at a crystal structure and predict its electronic behavior from first principles, does not exist for quasicrystals. Not fully, not yet. For 40 years, the most successful approach has been to work in the higher dimensional superspace and project the results back down to 3 dimensions. And that works. But it means that every time you want to understand a quasicrystal, you have to leave the 3-dimensional world and do your thinking somewhere else, in 6 dimensions, in a space that may or may not be physically real. The physics of quasicrystals is, at its mathematical core, physics that does not live in the space you inhabit. Now here is the part that I think connects this story to something larger, something that goes beyond crystallography. In 2023, a retired print technician from Bridlington, Yorkshire, named David Smith, a man with no formal mathematics training, no PhD, no university affiliation, discovered a single tile shape that tiles the plane aperiodically. 1 tile, not 2, like Penrose. 1. The shape is a 13-sided polygon, built from 8 copies of a kite from a hexagonal grid, and it was nicknamed the Hat because if you squint, it looks like a small fedora. Smith had been playing with tiles for decades, cutting shapes out of cardboard, testing them with the Polyform puzzle solver software, and in November 2022, he noticed that this particular shape seemed to fill space without ever repeating. He contacted Craig Kaplan at the University of Waterloo, who brought in Joseph Myers, a Cambridge-trained mathematician, and Chaim Goodman Strauss at the National Museum of Mathematics. Together they proved that Behat is an Einstein, German for one stone, a single tile that can only tile the plane aperiodically. The preprint appeared on March 20th, 2023, and within a week, Smith had found another related shape, the spectre, which tiles aperiodically without even needing mirror reflections. The proof that Berger achieved with 20,426 tiles in 1966, that Penrose achieved with 2 tiles in 1974, was achieved with a single tile by a hobbyist in a kitchen in Yorkshire in 2023. And the reaction of the mathematical community was not ridicule, it was celebration. Because by 2023, unlike 1982, the idea that non-periodic order is real, important, and potentially fundamental was no longer controversial. Shechtman had won. The definition had been rewritten. The impossible had been accepted. And here is the irony that I think Shechtman himself might appreciate. The scientific establishment that ridiculed him for finding impossible symmetries in a laboratory was now celebrating an amateur for finding impossible tilings at his kitchen table. The pattern had repeated one more time, but with the polarity reversed. In 1982, the establishment rejected the outsider's discovery. In 2023, the establishment embraced the outsider's discovery. The difference was not in the quality of the work. The difference was that Shechtman had already paid the price of changing what was acceptable. But the questions that the impossible raised have not been answered, and they are not purely theoretical. Quasicrystals are already in your life, in ways you have never been told. The strange properties of aperiodic order turn out to have practical consequences that are quietly transforming material science. Because quasicrystals are weird. They are metals that do not conduct electricity like metals. The electrical resistivity of an aluminum palladium rhenium quasicrystal at room temperature can reach 10,000 to 20,000 microohm centimeters, 2 to 4 orders of magnitude higher than ordinary crystalline metals. That is not a minor discrepancy. That is the difference between a copper wire and a ceramic. And the resistivity increases as you improve the crystal quality. In a normal metal, fewer defects means better conductivity. In a quasicrystal, fewer defects means worse conductivity. The better the aperiodic order, the harder it is for electrons to move. This is backwards. This is the opposite of how every other metal in the universe behaves, and it is a direct consequence of the non-periodicity, because the electronic wave functions in a quasicrystal have no block states to propagate through, no repeating unit cells to carry them forward. The electrons are, in a sense, lost. They cannot find a rhythm in a structure that has no period. This makes quasicrystals useful for things that sound contradictory. Low-friction non-stick coatings, because quasicrystalline surfaces have unusually low surface energy. Thermal barriers, because their poor thermal conductivity makes them excellent insulators despite being metallic. Sandvik, the Swedish toolmaker, produces a quasicrystalline strengthened maraging steel used in razor blades and surgical needles, where the quasicrystalline precipitates harden the steel without making it brittle. There is active research into quasi-crystalline thermoelectric materials, which convert heat into electricity, because the combination of metallic electronic structure and glass-like thermal conductivity is exactly what thermoelectric efficiency requires. And then there are the quantum effects, the ones that keep physicists up at night. How does a quasi-crystal grow? The empire problem remains unsolved. The mechanism by which atoms find their correct aperiodic positions without access to global information is not understood. The Cutton project framework works as mathematics, but whether the higher dimensional lattice describes something physically real or is merely a computational convenience is a matter of active debate. The community has not reached consensus on whether quasicrystals are thermodynamically stable at zero temperature or are only entropy stabilized at high temperature. And the physics is still moving. In August 2023, a team at MIT and the University of Toronto, led by Aviram Uri, published a paper in Nature, volume 620, describing superconducting states in moire quasicrystals, twisted layers of two-dimensional materials that form quasi-periodic patterns at specific angles. Moire patterns are what you see when two regular grids are overlaid at a slight angle. Those shimmering interference patterns that appear in screen doors or stacked fences. When two sheets of graphene, single atom-thick layers of carbon, are twisted at specific magic angles, they create periodic moire superlattices that host superconductivity. But when the twist angle is irrational, when it cannot be expressed as a ratio of small integers, the moire pattern becomes quasi-periodic. And Uri's team found that superconductivity persists. Electrons in a non-repeating lattice, without block states, without the standard mathematical framework that physicists use to describe cooperative quantum phenomena, still manage to form Cooper pairs and flow without resistance. The golden ratio appears in the twist angle, and the superconducting state exists in a geometry that should not support it. That result is still being digested by the condensed matter community. Its full implications may take years to work out. In October 2025, Sergei Alyatkin at Skoltech and collaborators at the University of Iceland, the University of Warsaw, and the Russian Academy of Sciences published in Science Advances a study of photonic quasicrystals, artificial Penrose tiling structures built from semiconductor microcavities that trap and control light. They created reconfigurable two-dimensional quasicrystal lattices for polaritons, hybrid quantum particles that are part light and part matter, and found that these quasi-particles exhibit fractal energy spectra and Anderson localization in the aperiodic lattice. Anderson localization is a quantum phenomenon where waves become trapped in disordered media, unable to propagate. But the quasicrystal is not disordered, it is ordered, aperiodically ordered, and the localization patterns follow the golden ratio, the same irrational number that controls the spacing of Penrose tiles. A number is telling photons where they can and cannot go. The golden ratio, which started as a curiosity in Penrose's kitchen table tile tutting, is now actively shaping the behavior of quantum particles in a laboratory. A third category of order. Again, the pattern keeps repeating. Not the tiles never repeat, but the story. Something is declared impossible. Someone finds it anyway. The establishment resists. Eventually, the evidence becomes undeniable. And then, instead of reckoning with what the discovery implies, the field absorbs it, names it, classifies it, and moves on without confronting the deeper question. The deeper question is this: if three-dimensional quasicrystals are best described as projections of six-dimensional periodic lattices, and if those quasicrystals form spontaneously in nature, in the violence of asteroid impacts billions of years before any human existed, then what does that tell us about the geometry of reality? Not the geometry we can measure, the geometry that exists whether we measure it or not. Because the cut and project method does not just work for quasicrystals. It works suspiciously well. It predicts atomic positions, diffraction patterns, phonon spectra, electronic properties. It is not a rough approximation, it is precise. And precision in physics usually means something. When a mathematical framework predicts experimental results to high accuracy, the historical precedent is that the framework is describing something real about the world. Maxwell's equations described electromagnetic waves before anyone had detected them. Dirac's equation predicted antimatter before anyone had seen it. General relativity predicted gravitational lensing before anyone had observed it. The mathematics was not just a calculating trick. It was pointing at reality. So when the mathematics of quasicrystals says that the atoms in a three-dimensional material are following the instructions of a six-dimensional lattice, the question that physicists should be asking, and largely are not, is whether that higher dimensional lattice is physically real. Not real in the sense that you can travel to it, real in the sense that it shapes the behavior of matter in 3 dimensions. Real in the sense that the structure of the physical world is determined in part by geometry in spaces you cannot access. This is not mysticism. This is a straightforward reading of the standard mathematical framework used by working crystallographers. And the fact that nobody discusses it publicly, the fact that the cut and project method is treated as a calculational convenience rather than a statement about reality, tells you something about the same institutional dynamics that tried to bury Shechtman in 1982. The establishment is comfortable with the mathematics as long as it remains a tool. The moment you suggest that the tool might be a window, that the higher dimensional lattice might be pointing at something real about the structure of space, the conversation becomes uncomfortable, not because the idea is wrong, because the implication is too large. I want to tell you one more thing, one detail from the research that I have not been able to stop thinking about, and then I will tell you what I think it all means. The Quasicrystal meteorite, the 4.5 billion-year-old rock that contained the first natural quasicrystals, formed in a collision between protoplanetary bodies in the early solar system. The pressures and temperatures were extreme, gigapascals of pressure, thousands of degrees, and in those conditions, atoms arranged themselves into a pattern with icosahedral symmetry, a pattern that never repeats, a pattern described by a 6-dimensional lattice, a pattern that the mathematics of our own civilization did not describe until 1974 and did not find in nature until 2009. Nature did not need Penrose, nature did not need Shechtman, nature did not need the cut and project method or superspace groups or the International Union of Crystallography. Before the Earth existed, before life existed, before there was anyone to observe or measure or define, matter was already assembling itself into structures that our science said were impossible. The forbidden symmetries were never forbidden. They were always there. The only thing that was missing was our ability to see them. And the artisans of Isfahan did not need Western mathematics either. They found their way to quasi-crystalline order through beauty, through the accumulated wisdom of a decorative tradition that valued 5-fold symmetry because it was beautiful, not because it was mathematically significant. They tiled their walls with patterns that would not be described by Western science for 5 more centuries. And when Western scientists finally described those patterns, they did not credit the artisans. They named the patterns after Roger Penrose. I am not telling you this to make a political point. I am telling you this because it reveals something about the nature of order itself. Order is not a human invention. It is not a mathematical construct imposed on passive matter. Order exists in the universe independent of our awareness of it. It existed before us. It existed in the collision of asteroids and in the tiles of medieval mosques. And the kinds of order that exist are not limited to the kinds we have defined. Our definitions are the bottleneck, not reality. The universe is more structured than we assumed, in ways we are only beginning to recognize, in geometries that extend beyond the 3 dimensions we can measure. And the history of quasicrystals is the history of how long it took us to notice. Dan Shechtman looked through an electron microscope on April 8, 1982, and saw a pattern that could not exist. 3 question marks in a notebook. He was told he was a disgrace. He was asked to leave. He was mocked by the most famous chemist in the world. His paper was rejected from a physics journal. He spent 10 years as the target of institutional contempt. And he was right. The crystal he found that morning has a structure that, according to the best mathematics we have, is a shadow of a 6-dimensional lattice, a projection from a space we cannot enter into a space we can measure. And the atoms in that crystal, every single one, sit at positions dictated not by their 3-dimensional neighbors, but by a pattern in a geometry that does not fit inside our universe. He did not discover a new alloy. He did not discover a new phase of matter. He discovered that the concept of order itself was incomplete, and that the universe had been using the complete version all along. 4.5 billion years ago, in the debris disk of a forming solar system, the same kind of crystal formed without anyone watching, without anyone defining what order is, without anyone saying what symmetries are allowed. The universe made a pattern that never repeats, and it has been making that pattern since before the Earth existed. The question is not whether forbidden symmetries are real. They are real. They are confirmed. They are sitting in a museum in Florence. The question is what it means that the best description of those symmetries requires more dimensions than the space they occupy. The question is where the extra information comes from. The question is what kind of universe permits matter to organize itself according to rules that do not fit inside the space the matter exists in. Nobody has answered that question, and nobody, as far as I can tell, is willing to ask it out loud. I want to come back to something I said near the beginning of this, because I think it hits differently now. I said that the cut and project method describes a 3-dimensional quasicrystal as a shadow of a 6-dimensional periodic lattice. I said that the atoms sit at positions determined by a higher dimensional geometry. And I said that this is not a metaphor, but the standard mathematical framework of the field. Let me tell you what that looks like in practice. When a crystallographer studies a quasi-crystal today, they do not work in 3 dimensions. They define a 6-dimensional superspace. They build a periodic lattice in that space, an ordinary hypercubic grid. They orient a 3-dimensional hyperplane through that 6-dimensional space at an angle determined by the golden ratio. And the points of the lattice that intersect or closely approach that hyperplane are the atomic positions in the real 3-dimensional quasicrystal. The calculations produce correct diffraction patterns. They produce correct atomic coordinates. They produce correct phonon spectra. The 6-dimensional model works better than any 3-dimensional model ever proposed. And what does that mean? What does it mean that the best description of a real physical material, a material you can hold in your hand, requires mathematics that takes place in a space with twice as many dimensions as the one you live in? One answer, the conservative answer, the one that most physicists would give you at a conference, is that it means nothing. The 6 dimensions are a mathematical convenience, a bookkeeping trick. The atoms are in 3 dimensions, the physics is in 3 dimensions, and the higher dimensional lattice is just a clever way to parameterize a complicated 3-dimensional structure. You should not read ontological significance into a calculational method. The 6 dimensions are not real. They are a tool. And maybe that is right. Maybe. But there is another possibility, and it is the one that I have not been able to shake since I started reading about this. The other possibility is that the 6-dimensional lattice is telling you something true about the structure of the physical world, that the reason it works so well is that it is pointing at a feature of reality that 3-dimensional physics cannot capture, that the atoms in a quasicrystal are not following 3-dimensional rules at all. They are following higher dimensional rules, projected into 3 dimensions, and the non-periodicity that Shechtman saw on his microscope screen is the signature of that projection, the fingerprint of a geometry that does not fit inside the space it inhabits. If that sounds extreme, consider the precedent. In 1908, Hermann Minkowski showed that Einstein's special relativity could be elegantly described by treating time as a 4th dimension, unifying space and time into a single 4-dimensional manifold. At first, many physicists treated this as a mathematical convenience, a bookkeeping trick, but over the decades, the 4-dimensional description proved so powerful, so predictive, so central to every subsequent development in physics, that the convenience explanation became untenable. Space-time is not a trick. It is the actual structure of reality. The extra dimension was real all along. General relativity went further. It said that the geometry of that 4-dimensional manifold is dynamic, that mass and energy curve it, that what we experience as gravity is actually the curvature of space-time. String theory proposes 10 or 11 dimensions. The standard model of particle physics uses gauge symmetries defined on abstract internal spaces. The history of fundamental physics is in large part the history of discovering that reality has more structure than the 3 spatial dimensions we perceive. Every time physics has been forced to add dimensions to its models, the dimensions have turned out to be describing something real. And now the mathematics of quasicrystals is asking us to do it again, not in the exotic regime of black holes or particle accelerators, or the first picosecond after the Big Bang, in a piece of aluminum alloy sitting on a lab bench, in a grain of meteorite recovered from a stream in Kamchatka, in a pattern of ceramic tiles on a mosque wall in Isfahan. The extra dimensions are not hiding at the Planck scale. They are showing up in the structure of ordinary matter, matter you can hold, matter that formed 4.5 billion years ago, in the dark, in the cold, in the violence of collisions between rocks that did not know they were doing mathematics. Think about what that means for a moment. It means that the structure of reality, the actual geometry in which atoms find their positions, may be richer than the 3 dimensions we experience. It means that the non-repeating pattern Penrose discovered on his kitchen table may be a clue to the dimensionality of space itself. It means that the forbidden symmetries Shechtman saw through his microscope may not be forbidden at all. They may be the natural symmetries of a higher dimensional geometry, appearing forbidden only because we are looking at them from inside a 3-dimensional slice. And it means that the question of how a quasicrystal grows, the question I have been asking throughout this entire story, the question that nobody has answered, may have a different character than we assumed. We have been asking how atoms follow a non-local pattern using only local information. But what if the pattern is not non-local? What if the pattern is perfectly local, but in a space with more dimensions than 3? What if the empire problem, the fact that placing one tile constrains tiles infinitely far away, is only paradoxical if you insist on thinking in 3 dimensions. In 6 dimensions, those infinitely distant tiles are neighbors. The non-locality is an illusion created by the projection. The atoms are not receiving information from far away. They are following the rules right next to them, in a space you cannot see. I am not proposing this as established physics. I am telling you that the mathematical structure points in this direction, that the people who built this field have acknowledged the question, and that the question has been sitting in plain sight since 1984 without ever being asked in front of a general audience. And the reason it has not been asked is the same reason Shechtman's discovery was suppressed, the same reason Penrose's tiles were ignored by physicists, the same reason the artisans of Isfahan were invisible to Western science. The implication is too large. The existing frameworks are too comfortable, and the people who would need to take the question seriously are the people who have the most invested in the frameworks the question would replace. I want to end with the meteorite, because I think it tells you everything you need to know about the nature of order in this universe. 4.5 billion years ago, before the Earth existed, before life existed, before there was anyone to observe or measure or theorize, 2 rocks collided in the debris disk around a young star. The collision generated temperatures above 1,200 degrees Celsius and pressures exceeding 50,000 atmospheres. And in that violence, atoms of aluminum and copper and iron arranged themselves into a structure with perfect icosahedral symmetry, a structure that never repeats, a structure whose mathematics requires 6 dimensions to describe, a structure that the civilization that would eventually arise on the 3rd planet from that star would spend the next 4.5 billion years failing to imagine, and then another 100 years actively denying was possible. The universe did not wait for us. It did not wait for Penrose to cut his tiles, or for Shechtman to turn on his microscope, or for the International Union of Crystallography to rewrite its definition. The universe was making quasicrystals in the dark, in the silence, in the space between forming planets, using a kind of order that our entire scientific civilization said could not exist. And the atoms followed the pattern perfectly, every one of them, as if they knew where to go, as if the blueprint existed somewhere they could read it, in a geometry with more room than 3 dimensions can provide. The tiles never repeat, the pattern has no period, and the blueprint, if there is one, lives somewhere we cannot go. The atoms follow it anyway.